Hi. So we're looking at this analog to digital conversion process. What it does is it converts this voltage into a number. There are two criteria, of course, one of which is how many bits this number will be. In other words, the resolution of the ADC. Another thing is what's the value of the reference? Are these two values the same? What would happen if, for instance, this was really small and this was really large? Then we would get small numbers here. And if this was really large, in fact, and it was close to this, then we would get our maximum value out of this. But if this value here exceeds this, then this will not go higher than its allowable maximum. In this case, 1023. So if this is 5 volts and this is 4 volts, then this will be the same output as if this was 4 volts and this was 4 volts. So you see, you can't wind this above the voltage reference and expect to get a higher number out. Just really clear about that. So that means that when we're looking at this model for it, we can't just assume that this model will work for anything. It'll only work within the range of the ADC and within the range of the voltage with reference to this voltage reference. So what does that mean in terms of this relationship here? If Vin is greater than Vref, then this would go to above 1, but this can never go above 1. Okay, so this isn't just an arbitrary formula, it is a model for something which is quite specific and unique. So that's what you've got to hold in your mind as we go into the next parts of the course. Now I've looked and said that there are 3 different voltage reference options. And down here where we have these different voltage reference options, we have our AVCC, which is a voltage which is powering up our analog to digital converter circuits, and that's typically the same as VCC. We have an internal 1.1 volt reference. Now, some of the other AVR microcontrollers have a slightly different internal voltage reference here. And then we can connect our own external reference voltage as well. So we might get a very powerful and stable voltage and use that as a reference. This cannot exceed, of course, our VCC voltage. And of course, the bits that select this are part of this AD-MUX register. And the 2 bits are ref S1 and ref S0. And you'll find them described in the data sheet. So let's have a look and say, what would be the commands to select the internal voltage reference? So in the data sheet, I'm looking at the internal voltage reference is this one here. The internal 1.1 voltage reference with external capacitor at a ref pin. So it's saying that you should connect a capacitor to this pin, typically a 0.1 microfarad cap. Okay, so what we would need to do then is we need to set both these bits to 1, which is what I've done here. Okay, so I'm just setting those 2 bits to 1. That's what we're doing. Now let's just have a look at the next question, because actually this is just a little bit tricky. It's not something you can just assume, but it says if you needed to change voltage reference during the program. So that means that we should never make any assumptions about the value of these 2 bits during the program. They may have been set up previously. We don't know the state that they're in. This is this whole concept of state. What happens is dependent upon what has taken place beforehand. And so we need to know that if we're going to assume that something has happened beforehand, we may end up being wrong, okay? Especially when multiple people work on a project. So what we need to do is if we're going to change the voltage reference during the program, then we need to make sure that both bits are set to what, or cleared to what they need to be. So in this case, I'm saying what would be the commands to select AVCC as reference? So that's 0, 1. So that requires us to make sure that we clear this bit and set this bit. This is really important. Again, this whole concept of state. What is happening at the moment in a program has been possibly affected by what has come before us. And so we cannot assume that this bit will be clear. Okay, so we should definitely purposefully clear it, and then we should set this bit as well so that we get our new reference. You see, we might have changed from this to this during the program. Okay, so just a little bit of a pointer out there. Now I just want to have a look at for instance, the voltage divider. What's going on here? We've got some different things here. We've got a light dependent resistor, which has got a negative characteristic here. Notice that it's a log-log type characteristic, okay? And so as the lux or illumination or the brightness of the light increases, then what happens is that the resistance goes down, okay? So that sort of makes sense. As something gets brighter, the resistance goes down a bit. And of course, what does that mean here is that if this, as the light level goes up, this resistance value goes down, then this voltage here will rise, okay? So therefore the output voltage will go up as the light level increases. Let's have a look at the NTC negative temperature coefficient thermistor, okay, for doing temperature sensing. Now you'll see some of them have got NTC written on them. Again, this is a logarithmic scale, okay? So as the temperature goes up, the resistance comes down. Often, you know, we might be working in just a part of the graph, but as you can see, as the temperature goes up, the resistance comes down. And so now you notice that I've changed this in the voltage divider. So I've put the variable element in this part of the voltage divider. So how's that going to affect our output voltage? So as the temperature goes up, this resistance goes down, and therefore this voltage here will go down as well, okay? Now, in both of these cases, this is a fixed value resistor. So nothing, these changes will not affect this. This will just stay static in its value. Here's another thing. We've got this linear or logarithmic. I don't know what my spelling was doing there, but I've just fixed that spelling to logarithmic. And typically around 270 degrees, sometimes 290 degrees. And so as you change this, it might go up one end and down the other end. So as the displacement of whatever object we have connected to this potentiometer changes, what's going to happen then is that the voltage here will change. This is exactly how sensors work in getting a change in some atmospheric, environmental condition. We change the resistance of a value. Quite common. Some sensors work with capacitance, okay, but the resistance ones are fairly common. So what that means is that this voltage in a voltage divider will change depending on how the value of this resistance has changed. If you're going to use a capacitive sensor, then it's going to require a different circuit. Okay, so now just one little note to finish this section off is if this is going to vary over a range, then what you're really interested in is about the center of the range that you're interested in. You might be thinking, oh, I'm going to vary this between, you know, closely around daylight, or I'm going to work mostly in the evening, dark, or I'm going to work in bright sunlight. So therefore you want to choose a resistance value for this fixed value resistor that's actually going to be close to the center of the range you're working at. And that just means that you'll end up getting a better swing of around this value here. As this changes, this voltage will swing best if this value here is close to about the center of the range you're measuring. And the same for a thermistor. That's typically what you do. You'd start with that. So if I was working over a range of -10 to 40 degrees, then finding out what the resistance is at 15 degrees would be quite useful, and I might use a value similar to that. Okay, so I'll just pause that there, and we'll come back to this in the next video. Cheers.